Hello and welcome. In this video, we're going to talk about how to factor polynomials, not just quadratics, but extending what we already know about how to factor quadratics to how to factor cubics using the difference of cubes, and how to really approach factoring any polynomial using various strategies. So let's go ahead and jump right in. So really what we're covering in this section isn't anything brand new. We're going to be applying what we have covered in previous sections and in previous courses to extend that a little further now that we're talking about polynomials and graphing polynomials. So these first couple examples really tie directly back to Algebra 1. So a couple of reminders, anytime we're factoring, the very first thing we always want to do is we want to check for the greatest common factor. So if we look at example 1, all three of these terms are divisible by x, or they all have an x in common. If I factor an x out, I get x squared minus 4x minus 5. And then we have to remember we need to attempt to factor what's left over. And this inside term, this trinomial here, does factor to x minus 5, x plus 1. So always start by factoring out the greatest common factor and then factor what's remaining. So go ahead and pause the video and work through 2 through 4 on your own, and then unpause the video and see how you did. So here I've factored the greatest common factor out of each of those terms. Now I'm going to factor what's left on the inside in blue. So on number 2, we have a difference of squares in y squared minus 16. So that's going to factor to y plus 4, y minus 4 with that 3y cubed out in front. Make sure you keep the factors. We're not solving here, we're factoring. Solving is coming soon, fear not. But for number 3, we can factor an x out, and then we have x plus 6 times x plus 4. And on number 4, we can factor 5z squared out first. That's the greatest common factor, and we're left with z plus 3 quantity squared, or you could have that written as z plus 3 times z plus 3. The next thing that we learned when we were factoring is that if you have 4 terms, still check for the greatest common factor first, but I noticed that all of these problems, the greatest common factor is 1 for 5 through 8. So if you have 4 terms, then you factor by grouping. So you group the first 2 terms together. I'm going to put a plus here, and then you're going to group the second 2 terms together. Make sure you don't turn this into a multiplication problem. Then you identify the greatest common factor in the first 2 terms, which is x squared, and the greatest common factor in the second 2 terms, which is going to be negative 4. And what's left if I factor x squared out is x plus 5. If I factor negative 4 out is x plus 5. We know we are correctly factoring by grouping since these 2 black sets of parentheses here match. So we're going to factor that out. And what's left is x squared minus 4. Now, anytime you get here, always ask yourself, can I factor more? Because we are factoring completely. And yes, we can factor more because x squared minus 4 is the difference of squares, and that factors to be x plus 2 times x minus 2. So go ahead and pause the video and work through 6 through 8 on your own, and then unpause the video and see how you did. So here we have factored all of these remaining terms. So I encourage you to pause the video so that you have enough time to check over all of the problems on this page. One quick thing I do want to point out though, remember that the difference of squares only works when it's a difference, when there's subtraction. Here on 7, this is a plus sign. This is not the difference of squares. And here on 8, this is a plus sign. This is not the difference of squares. We can't factor this using real numbers, so we aren't going to factor it at all. Okay, let's extend this idea to something new. We noticed a pattern with the difference of squares. What happens if we have the sum or difference of cubes? Okay, so there are 2 tricks that apply to factoring perfect cubes, and they're really the same trick. It just depends on if you're adding perfect cubes or subtracting. So unlike perfect squares, this works both with addition and subtraction. And the way that it goes is if you identify that you have something cubed plus something cubed, like you could evenly cube root each term, that can be factored to whatever the cube root is, a and b, a plus b, times a squared minus a times b plus b squared. Similarly, if it's negative, you just have a negative sign in the first set and 2 positives in the other. So let me show you what I mean. On number 9, we have 2 perfect cubes. We have x cubed, and 125 is the same thing as 5 cubed. So in this case, you can think of a as x and b as 5, because those are the cube roots of what's there. So according to this formula here, the difference of cubes, I'm going to have x minus 5, that's a minus b, times a squared, which is x squared, plus a times x, which is 5x, and I understand it's negative 5x, but we are going to do the opposite sign that we just did, plus b squared, which is 5 squared, which is 25. The way that the signs work, there's this little acronym here that might help you, is that the signs are SOAP. The first sign is the same as it was in the original problem. The second sign is always the opposite of whatever that first sign was, and the last sign is always positive. So let's go ahead and look at number 10. And remember, the very first thing we always do is check for that greatest common factor, which in this case looks like it's going to be x squared, and 16 and 54 are both divisible by 2. So if I factor 2x squared out first, that's going to give me 8x cubed plus 54 divided by 2, 27. So now I have two perfect cubes. So I'm going to ask myself, in this case, what's A? A is 2x, because if I put 2x to the third power, I would get 8x cubed. What's B in this situation? B is 3. So no matter what in my final answer, I'm still going to have this 2x squared up here. That was my greatest common factor. But inside, I'm going to have A plus B, 2x plus 3. And it is plus because this was a plus. Times a squared, 2x squared is 4x squared, minus, because opposite sign, a times b is 6x, plus, always positive, b squared, which is 9. And this is the completely factored form that we have for our perfect cubes. Okay, these two examples I think you can do without my help, but I'm going to just address what we're talking about here. These are higher powered exponents, but that doesn't change anything about how we factor. We can still use the difference of squares. We can still use factoring out the greatest common factor. The trick here, or the point that I want to point out here, I guess, is that we are factoring something that is in quadratic form, and it's in quadratic form because we have a times something squared plus b times something plus c as a factor after we complete our factoring. But this really doesn't change anything that we're doing here. So I'm going to encourage you to pause the video and factor these completely, and then unpause the video and see how you did. So hopefully you noticed on number 11 that this is the difference of squares. So to factor this, 16x to the fourth is going to be 4x squared minus 9 and 4x squared plus 9, because 16x to the fourth is a perfect square and 81 is a perfect square. But don't forget, this can factor more. This is also the difference of squares, so 2x minus 3 times 2x plus 3 times the 4x squared plus 9. On number 12, the first thing that I notice is that there's a greatest common factor of 2x to the fifth. If I factor that out, I'm going to have x to the 8th plus 5x to the 4th plus 4. And even though this looks a little different with my x to the 8ths and my x to the 4ths, the idea here is still just like factoring a quadratic. So I'm asking myself, what makes x to the 8th? Well, that's going to be x to the 4th times x to the 4th. And what multiplies to be 4 that adds to be 5? Positive 4 and positive 1. And notice, since these two, we have perfect squares here, but since they're the sum of perfect squares, they don't factor in the same way that we had factoring occur on number 11, because it's not the difference of squares. So we're really just pulling all of those factoring tools together so that we can factor anything that's thrown our way. The only thing that should be completely brand new are those perfect cubes, and it's just going to take some practice to really learn and understand that formula. Now that we know how to factor, or that we can factor a little bit stronger than we could before, let's talk about the factor theorem and how that ties to a polynomial. Okay, the factor theorem says that when we're dividing polynomials, as we did in the previous section, if something is a factor, then the remainder is going to be equal to 0. That makes sense. If I divide 24 by 4, I get 6, and there's no remainder because 24 evenly divides by 4. So the same idea is here. If we divide and we don't have a remainder, that means that something divides in evenly. Well, since we learned how to use synthetic division in the last section, we can actually use synthetic division to test to see if something is a factor. If the remainder is 0, so that's the key thing that we're looking for, if the remainder is 0, that means it's a factor. If the remainder is not 0, then it's not a factor. So since we know how to use synthetic division, we can actually use synthetic division to assess if something is a factor. So I'm going to write -4 since the term I'm factoring out, or I'm seeing if it's divisible, is x plus 4. I'm going to write the coefficients. I'm going to bring them down and multiply and add and multiply and add. And here we get that the remainder is 0. That means that x plus 4 is a factor. And I just want to take this one step further. What we're saying is x squared plus 3x minus 4 is equal to x plus 4 times whatever's left here. And how do we write this as a factor? Well, we decrease the exponent by 1, so that's just x minus 1. And we could multiply this quadratic out to prove that these two things are equal. So I actually am going to slightly modify this problem here. I'm going to put a 2 here. So now I want you to pause the video with the 2 there. Go ahead and set up the synthetic division and see if x plus 5 is a factor. Then unpause the video and see how you did. So here we get a remainder that is not 0. And since the remainder is not 0, x plus 5 is not a factor. So let's extend this one step further, kind of like we did on number 13, and verify that something is a factor and then use that to factor completely. Okay, so the first thing I want you to do is pause the video and show, so I'm telling you, spoilers, the remainder should be 0 for both of these problems. So go ahead and show that each indicated term is a factor using synthetic division. So check and make sure you had placeholders where you were missing terms, but both of these do, in fact, have a remainder of 0. So what we have said so far is that x to the 4th plus 3x to the 3rd minus x minus 3, we have found one factor, which is x plus 3. Similarly, over here, we've said that x to the 4th minus 2x to the 3rd plus x minus 2, that it has a factor of x minus 2. Now, let's see if we can factor what's left. Well, this was x to the 4th, so this is now x to the 3rd plus 0x squared plus 0x minus 1. And we can factor that using perfect cubes. So in this case, a is x and b is 1. So this is going to factor to be x minus 1 times x squared plus x plus 1. So that's using that perfect cube rule that we learned in the first part of these notes. So go ahead and pause the video and try and finish 16 off on your own, and then unpause the video and see how you did. All right, so this should simplify to be x cubed plus 1, which is going to factor really similarly to over here, x plus 1 times x squared minus x plus 1. So this is going to be x plus 1, x squared minus x plus 1. And that is factoring completely. So now we can use the fact that we understand how to use synthetic division to test for factors to factor something completely and maybe make something that started a little complicated, like our polynomials at the beginning of these problems, to factor all the way through. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.